Okay, so now we will solve remaining questions of our booklet or previous year gate questions. The first question says, in terms of speed of rotation of impeller N, discharge Q and change in total head H through the machine, the specific speed for the pump is. Okay, so I have already told you the formula. Specific speed for the pump N in terms of N, Q and H is N root Q divided by H raised power 3 by 4. Answer. Okay, next, Kaplan turbine. Okay, so Kaplan turbine is we have classified as low head axial flow turbine. Answer should be B. Next question, if there are m physical quantities and n fundamental dimensions in a particular process, the number of non-dimensional parameter, okay, this is from Buckingham pi theorem, number of non-dimensional parameter, that means number of pi terms. Okay, so because there are m number of physical quantities and n fundamental dimensions, so total number of pi terms will be equal to m minus n non-dimensional terms. Getting this? Okay. Next question, in a Pelton wheel, the bucket peripheral speed is 10 meter per second. The water jet velocity is 25 meter per second. Bucket peripheral speed means u is given as 10 meter per second. Water jet velocity, that means v1 is given as 25 meter per second, and volumetric flow rate is 0.1 meter cube per second. Q is given as 0.1 meter cube per second. The jet deflection angle is 120 degree. Okay, so we have got the Pelton wheel like this. Okay, the inlet will be here. Okay, so this V1 will be equal to VW1. We have already discussed. The outlet, this is V2, this is VR2, like this. Okay, so the jet deflection angle is 120 degree. That means this angle is given as 120 degree. Okay, this angle is jet deflection angle. Okay, so obviously this angle will be 60 degree. Okay, now we have to determine what flow is ideal, the power developed. So power developed, as we have already discussed, is m into VW1 U1 minus VW2 U2, and that was further derived as rho Q into U V1 minus U into 1 plus K cos beta. Okay, you can directly remember this formula. This will be very helpful for you. If you want, you can see the proof in the theory lecture. Okay, we have already derived this, rho Q U V1 minus U into 1 plus cos beta. So just put the value. So this will be 1000 into Q is 0.1 into U, which is 10, into V1 minus U 25 minus 10 into 1 plus K. The value of K is not given, so take it as 1. Cos of beta, cos of 60 degree. So this will be equal to 22,500 watt or 22.5 kilowatt. Okay, so answer should be C, 22.5 kilowatt. Getting this or not? Okay, next question. The phenomena is modeled using n dimensional variable with k primary dimension. Number of non-dimensional variable, again number of pi terms is equal to n minus k. That's it, simple. Okay, और बकिंघम पाई थ्योरम से जो क्वेश्चंस आए हैं वो यहीं तक आए, इसके ऊपर लेवल के नहीं आए. हाउएवर वी हैव डिस्कस्ड द न्यूमेरिकल पार्ट आल्सो कि किस तरीके से हम पाई टर्म डिटरमाइन कर सकते हैं. Okay, next question. The hydraulic turbine develops 1000 kilowatt power for a head of 40 meter. Okay, power is given, head is given. If head is reduced to 20 meter, the power developed will be. Okay, so we have to establish the relation between the head and power. So what we can do is we can put the head number first, which is h1 by n1 square d1 square is equal to s2 by n2 square d2 square. Okay, now initially the power P1 is given and head H1 is given as 40 meter. Okay, so from here this will be equal to this N1 by N2. Okay, now turbine is same, so diameter will be same. N1 by N2 will be equal to under root of H1 by S2. Getting this? Okay, so this will be under root of 40, H1 is 40, S2 is given as 20. Okay, so this will be equal to root of 2. Further we want to determine power developed. Okay, so putting power number P1 by N1 cube D1 raised power 5 is equal to P2 by N2 cube D2 raised power 5. Again diameter will be cancelled and we will get what? P2 is equal to P1 into N2 by N1 whole cube. Okay, so this will be equal to P1, which is 1000, into n2 by n1. n1 by n2 is root 2, n2 by n1 is 1 by root 2 to the power 3, that means 1 by 2 to the power 3 by 2. So this will be equal to 354 kilowatt. Answer. So answer should be B. Clear or not? Okay. Next question. In order to have maximum power from Pelton turbine, the bucket speed must be. Okay. So for maximum power, I have already told you, for maximum power or maximum efficiency, for the bucket speed, this rho is equal to 0.5. This is for maximum power. We have drawn the curve also, if you remember, for maximum power. Okay, and this rho is nothing but U by V1. This is equal to 0.5. Therefore, U will be equal to V1 by 2. Okay, that means equal to half of the jet speed. That's it. Getting this? Okay. Next question. Kaplan water turbine is commonly used when the flow through the runner is. Okay. So Kaplan turbine, as I have told you, is used when the flow through the runner available head is less than 10 meter. Getting this? Low head turbine. Next, consider two hydraulic turbines, identical specific speed and effective head at inlet. If the speed ratio N1 by N2 of the two turbines is 2, then the respective power ratio is. Okay. So identical specific speed Ns is equal to N1 root P1 by H1 raised power 5 by 4 is equal to N2 root P2 by S2 raised power 5 by 4. That's it. From here, P1 by P2 is equal to N2 by N1 whole square. Okay, so this will be 1 by 2 square or 0.25. Answer. Simple. Okay. Next question. The blade and fluid velocities for an axial turbine are shown in figure. Okay. So these are the blade velocity is given as 150 meter per second, and these are the fluid velocity. Here at entry it is 300 meter per second at an angle 65 degree from horizontal, and at exit it is 150 meter per second. Okay. The magnitude of absolute velocity at entry is 300 meter per second. Okay. Absolute velocity, that means V1 is given as 300 meter per second. Okay. U is given as 150 meter per second. Okay. The angle is 65 degree to the axial direction, while the magnitude of absolute velocity at exit V2 is given as 150 meter per second. The exit velocity vector has a component in downward direction. Okay. This is having a component in downward direction. Given the axial velocity is same at entry and exit. Axial velocity, that means U1. Axial velocity means Vf1 is equal to Vf2 is equal to Vf. This is same at entry and exit. We have to determine the specific work. Getting this? Okay. So first of all, let us draw the velocity triangle, and we will try to draw it according to our convention. I will turn this anti-clockwise. We are having this inlet velocity vector like this. V1 is equal to 300 meter per second. Okay. Then there will be VR1 and Vf1. Okay. And this angle is given as 65 degree. That means the angle in this, the angle with vertical, this angle is 65 degree. Getting this or not? So don't get confused with this. But we actually want this angle. Okay. So this angle is actually 25 degree. This angle is 25 degree alpha. Getting this or not? Okay. So this will be U1 and this will be VW1. This is inlet velocity triangle. Okay. Now what about outlet velocity triangle? So here this will be V2, Vf2, VR2. Okay, so this will be U2 and VW2. Okay, so this is our inlet and velocity outlet velocity triangle for this particular blade. Okay. So what we have to determine here is this specific work. Okay, and what is the formula for specific work? We know what this is equal to VW1 plus minus, and in this case obviously plus VW2 into U. Okay, because this is a specific work, so no M term here. Okay, now for this we will have to determine VW1 and VW2 from here. So how can we determine this VW1? So this VW1 is equal to V1 cos of 45, simply from the triangle V1 cos 25, V1 cos of 25, okay, or this is equal to V1 is given as 300 cos 25, so this will be equal to 277.16 meter per second. First thing, okay. Similarly, you can determine this VF1. VF1 is nothing but V1 sine of 25, okay, so this will be 300 sine 25, so this will be equal to 114.8 meter per second. Getting this? Okay, now one more thing is given, that VF1 is equal to VF2, so this is also equal to VF2. Okay, now what will be VW2 now? So this VW2 is equal to, okay, so VW2 will be this will be this is VW2, okay, component of this V2 in horizontal direction is VW2, and this will be U2. Getting this? Okay, now what will be this VW2? This will be equal to under root of V2 square minus VF2 square. Okay, so just put the value. So this will be under root of V2 is given as 150 square minus 114.8 square. Okay, so from here this VW2 will be equal to 96.53 meter per second. Getting this? Okay, so what will be specific work? So this work will be equal to VW1 277.16 plus 96.53 into U, okay, and U is given as how much? U is given as 150, so into 150, so this is specific work from here will be equal to 56.05 kilojoule per kg. Answer. Getting this or not? Okay, now next question. Cavitation in hydraulic reaction turbine is most likely to occur at the turbine. Okay, where does the cavitation occurs in the reaction turbine? So in Francis turbine, as we have seen, the pressure is minimum at the rotor exit, okay, because when it leaves the rotor, the pressure is even below atmospheric pressure, and that's why we use draft tubes so as to bring that pressure in the level of atmospheric pressure. Okay, so the cavitation can occur when the pressure is very less, so it will be at rotor exit. Getting this? Okay, next, specific speed of Kaplan turbine ranges between, this I have already told you, 300 to 600. Next question, at a hydroelectric power plant site, available head as flow rate and available head and flow rate are 24.5 meter and 10.1 meter cube per second respectively. Okay, that means H1 H is given as 24.5 meter and Q is given as 10.1 meter cube per second. If the turbine is to be installed, is required to run at 4 RPS, N is given as 4 RPS, okay, with an overall efficiency is given as 90%, then the suitable type of turbine for this is. Okay, so in order to determine suitable type of turbine, what we can do is we can determine specific speed, then on the basis of a specific speed we can select the turbine. Okay, so this can be the process. Now what is the specific speed? We know Ns is equal to N root P upon H raised power 5 by 4. Getting this? Okay, now this N, we have the value of N, we have the value of H here, we don't have the value of P. Now what we can do is, the overall efficiency is given, and from this overall efficiency the value of this power, shaft power, can be determined. So overall efficiency is shaft power or P upon rho g QH. Okay, so from here this P will be equal to, overall efficiency is 0.9 into rho g QH, rho g is 9810 into Q is 10.1 into head is 24.5, so this will be equal to 2184.7 kilowatt. Getting this? Okay, so just put the value. Now this N is given as 4 RPS, but here this N should be in terms of RPM, then only we will get this NS in terms of RPM. So this will be 4 into 60 into under root of P, which is 2184.7 divided by H raised power 5 by 4. H is given as 24.5 to the power 5 by 4. Okay, now this NS from here will be equal to 205 RPM. Okay, so now on the basis of this specific speed we can define the turbine, we can decide the turbine. So for the specific speed between 60 to 300 RPM, this we have already seen in the classification, we use what? Francis turbine. Okay, so this ranges between 60 to 300 RPM, so we will use the Francis turbine here. Getting this now? Okay, next question. A large hydraulic turbine is to generate 300 kilowatt at 100 rpm under a head of 40 meter. Okay, that means for this prototype, power is given as 300 kilowatt, N is given as 100 rpm, and head is given as 40 meter. Okay. For initial testing, the model is prepared with scale 1:4, and this model operates under a head of, that means head of model is given as 10 meter. We have to determine the power generated by the model, okay, by the model, and scale is given, that means D model by D prototype, this is given as 1:4. Okay, very simple to determine. So for this, what we can do is we can put the head number first, H upon N square D square for model is equal to H upon N square D square for prototype. Just put the value. Okay, now here this H for model is given as 10 meter divided by Nm square into Dm square is equal to H for prototype is given as 40 meter divided by Np square 100 square into, now this dp can be written as 4 times of dm, this dp is equal to 4 dm. Okay, so this will be 4 dm whole square. Okay, so from here this dm square will be cancelled out, and you will get what, Nm will be equal to 200 rpm on calculation. Getting this now? Okay, now further we want to determine the power generated. So put power number P by n cube d raised power 5 for model is equal to P by n cube d raised power 5 for prototype. Okay, so from this we will get the value. We have the value of for model we have the value of n and m, and for prototype we have the value of n, d and p. Okay, for model n and d, for prototype n, d and p, all these values are there, so we can determine the power for model, which is equal to 2.34 kilowatt. That's it. Getting this now? Simple. Next question. Okay. The inlet angle of runner blades of a Francis turbine is 90 degree. The blades are so shaped that the tangential component of velocity at blade outlet is 0. The flow velocity remains constant throughout the blade passage and is equal to half of the blade velocity at runner inlet. The blade efficiency is. Okay, so we have given the inlet angle of the runner blade of Francis turbine is 90 degree. Inlet angle of runner blade is 90 degree. That means the angle of VR1 with horizontal. So inlet velocity triangle will be like this. This is V1. This angle of VR1 is 90 degree. Okay, and this is also vertical component of V1, so this will also be equal to VF1. First thing. Second thing, the horizontal component of V1 will be equal to VW1, and this distance between V1 and VW1 is also equal to U. Getting this now? Okay, so this is our inlet velocity triangle. Now, what about outlet velocity triangle? Blades are so shaped that the tangential component of the velocity of blade at outlet is 0. So, okay, tangential component of velocity, that means VW2 is 0. Getting this or not? So, for VW2 is equal to 0, so outlet velocity triangle will be like this. So, here this will be VR2, okay. VW2 should be equal to 0, that means V2 should be horizontal. Getting this now? VW2 is nothing but horizontal component of V2. So this V2 should be, V2 should be vertical line. So this V2 should be equal to VF2. Getting this? Okay. And this will be equal to U2. Simple. This will be U1. समझ में आएगी नहीं यार? Okay. Inlet angle दिया हुआ है. For inlet angle for the runner blade is 90 degree. That means inlet runner blade का angle means the angle of VR1 with horizontal वो 90 degree है. Okay, that means this VR1 will be vertical, and this V1 will have two components. The vertical component will be equal to VR1, which is VF1, and horizontal component will be equal to VW1, which is also equal to U1 in this case. Okay, similarly exit में क्या बोल रहा है? For exit this VW2 is equal to 0. Okay, tangential component of velocity at blade outlet is 0. VW2 is 0. VW2 0 का मतलब क्या हुआ? That means this V2 is vertical. Getting this now? Okay, that means VR2 is like this, and this V2 will be equal to VF2, and this is U2. Clear or not? Okay, now the flow velocity remains constant throughout the blade. That means Vf1 is equal to Vf2. Flow velocity is constant and is equal to half of the blade velocity at runner inlet. Half of the blade velocity at runner inlet is equal to U1 by 2. Getting this or not? Okay, the blade efficiency of the runner is, okay, so what is the blade efficiency? So blade efficiency, already I have told you that output of blade, ratio of output to input of the blade. ओके, और पैटर्न व्हील में हमने ब्लेड एफिशिएंसी डिफाइन की भी थी, याद होगा तो, दैट आउटपुट ऑफ द ब्लेड वाज इक्वल टू द वर्क डन, आउटपुट ऑफ द रनर विच वाज इक्वल टू वर्क डन, विच वाज m into VW1 plus VW2 into U. Okay, and inlet to the blade was kinetic energy there. Inlet to the blade was complete kinetic energy because it was an impulse turbine. But this Francis turbine is not an impulse turbine, so inlet will not be completely in the form of kinetic energy. So what we can do here is we can put another formula. The output obviously is equal to the work done, which is equal to VW1 into U1 into M. Okay. Now what about inlet? So we don't have the direct value of inlet. So what we can do is, this turbine is developing a work of this much VW1 U1, M VW1 U1, and after developing the work, the rest of the energy is converted to kinetic energy V2. Getting this or not? Okay, so assuming no other losses in the turbine, the inlet velocity, the inlet energy I should say, will be equal to M into VW1 U1 plus half M into V2 square. ये चीज समझ में नहीं आ रही? इनपुट एनर्जी कौन सी है? इनपुट एनर्जी इज इक्वल टू दिस आउटपुट एनर्जी, और इनपुट एनर्जी इज इक्वल टू टोटल वर्क डन, यहाँ जितना वर्क हमको मिल रहा है इम्पेलर में, विच इज VW1 U1, इसके अलावा जितनी एनर्जी आउटपुट गई है इन द फॉर्म ऑफ काइनेटिक एनर्जी. गेटिंग दिस? ओके, सो दिस विल बी टोटल एनर्जी एंड दिस इज द total input energy, sorry, this is total output energy, this is total input energy. Clear or not? Okay, now so this can be written as what? So this will be VW1 U1 divided by VW1 U1 plus V2 square by 2. Getting this? Okay, now further this can be written as what? Now this VW1 is equal to U1, VW1 is equal to U1, so this will be U1 square upon U1 square plus V2 square by 2. Now what is V2? V2 is equal to VF2. Getting this? Okay, and this VF2 is equal to again U1 by 2. Okay, so this V2 is actually equal to U1 by 2. Getting this? Okay, so this will be equal to V2 square, which is equal to U1 by 2, U1 square by 2 square. Okay, now there is one more 2 here, so into 2. Okay, so this will be equal to U1 square upon U1 square plus U1 square by 8. Okay, so this will be equal to 8 by 9. Okay, or you can say 88.8 or 89% approximately. Okay, so answer should be this 89%. Getting this or not? Simple question. Okay, now next question is again very simple. I am leaving it up to you. Okay, you can do it yourself. The answer should be C. Simple model prototype question. Next question, the match the column. Centrifugal compressor, obviously we have not done centrifugal compressor, but still we can solve this. Next is centrifugal pump. Okay, centrifugal pump is something related to priming. Okay, what is priming? Priming in order to avoid cavitation, in order to avoid the formation of bubble in the starting of the pump. What we do is, अगर आपने देखा होगा, अपने घरों में भी देखा होगा, पंप स्टार्ट करने के पहले वी पुट सब वाटर हियर, वाटर दे, जो इनिशियली जब हम स्टार्ट करते हैं तो उसमें हम कुछ वाटर डालते हैं. ओके, सो डैट कि उसमें से वाटर बबल पूरे बाहर हो जाए. दैट प्रोसेस नथिंग बट प्राइमिंग. ओके, सो सेंट्रीफ्यूगल पंप इज समथिंग रिलेटेड टू प्राइमिंग. पेल्टन व्हील इज प्योर इम्पल्स टर्बाइन. Kaplan turbine is an axial turbine. So obviously this centrifugal compressor is something related to surging, and surging is actually an operating point जहाँ पर हमारा head maximum रहता है and flow minimum रहता है. The operating point where the head is at its peak, we are getting maximum head with minimum discharge, with minimum flow limits. Getting this? Okay, that is known as surging. Okay, so answer should be 2 3 4 1. 2 3 4 1. Answer should be A. Getting this? Okay. Next question. Okay, a good question. Water having a density of 1000 kg per meter cube issues from nozzle with a velocity of 10 meter per second, and jet strikes a bucket mounted on the Pelton wheel. The wheel rotates at 10 radian per second. Okay, the mean diameter or of the wheel is 1 meter. The jet is split into two equal streams by the bucket such that each stream is deflected by 120 degree as shown in figure. Friction in the bucket may be neglected. Magnitude of torque exerted by the water on the wheel per unit mass flow rate of the incoming jet is. Okay, so what it is saying in the question is, water is having the density, not a new thing, of 1000 kg per meter cube, issues the nozzle with the velocity of 10 meter per second. That means the value of the V1 is given as 10 meter per second. Getting this? And the jet strikes the bucket mounted in the Pelton wheel. This is incoming jet striking the bucket. The wheel rotates at 10 radian per second. Omega is given as 10 radian per second. Okay, and from this omega, obviously you can determine U is equal to omega into R. Okay, we will determine this. So this will be 10 into the diameter is given as 1 meter, so R is 0.5, so this will be equal to 10 into 0.5, which is equal to 5 meter per second. Okay, so from this omega and R we can determine this U. Second thing, now the jet is split into two equal streams by the bucket. So this jet is further split into two equal streams, and each stream is deflected by 120 degree as shown in figure. Okay, now the friction in the bucket may be neglected. Magnitude of the torque exerted. So we want to determine the torque exerted. So for torque, obviously we want to determine the force first, because suppose if this is a Pelton wheel turbine, this is the Pelton wheel turbine. Okay, and if we want to determine the torque, obviously we will have to first determine the tangential force. Whatever is the tangential force, that force into radius will be equal to torque. Okay, so for that first we will have to determine the force. Okay, and what is the formula for force? Same thing, in order to determine the work done, we have derived the work done, and that work done was equal to F into U. Okay, so from that work done formula, if you remember that work done formula, and if you remove U from there, you will get what? Force, and that force will be equal to M into V1 minus U into 1 plus cos beta 2. Getting this? Now for per unit mass flow rate, this will be F by M. For per unit mass flow rate, this will be V1 minus U into 1 plus cos of beta 2. Getting this or not? Okay, now this question is very simple now. Now what is the value of beta 2 now? Okay, so this is our incoming jet, this is the outgoing jet, and the value of this beta 2 if we want to determine, so this will be, this is our incoming inlet velocity triangle. In which V1 will be equal to VW1. Getting this? Here we have U1 or U, you can say, and here we have VR1, which is equal to V1 minus U. Okay. Now what about outlet velocity triangle? So outlet velocity triangle is like this. So this will be VR2. Okay, this angle is V2, sorry, this is V2 and this is VF2. Okay, now this angle is beta 2, and this beta 2 obviously will be equal to this angle beta 2 will be equal to 180 minus 120, which is equal to 60 degree. Getting this? Okay, yes, this angle is beta 2 is equal to 60 degree. Getting this or not? Okay, now what I think we have everything now, so we can determine this. So this will be equal to 10 minus U is 5 into 1 plus cos of 60 degree. That's it. So from here this force is equal to 7.5. Getting this now? Okay, Newton meter.
Newton, sorry, 7.5 Newton. Now torque will be equal to 7.5 into radius, which is equal to 0.5, diameter is 1 meter, so this will be equal to 3.75 Newton meter per kg second, because this is per unit mass flow rate. Getting this? So this will be our torque, 3.75. Answer should be D. Clear or not?